Good morning, everyone. Myself P. Venkateswar Reddy. I am from Tripoli 4th year and 8th semester. My PIN number is 21955 and today we are discussing about the subject known as electrical and hybrid vehicles. In this, the current topic is a survey on driving prediction techniques for predictive energy management of plug-in hybrid electric vehicles. So, as for when we go into the concept, the driving prediction techniques, simply known as the DPTs, are used to forecast the distributions of various future driving conditions, simply known as FTC, like velocity, acceleration, driver behaviors, etc., which totally consists of the normal universal physics and human psychology. And the quality of prediction results has great impacts on the performance of corresponding predictive energy management strategies, simply known as PEMSs. We can say example as fuel economy, lifetime of battery, etc. This survey presents a comprehensive study on existing DPTs. Firstly, a review on prediction objectives and major types of prediction algorithms are presented. Then, a comparative study on various prediction approaches is carried out, and suitable application scenarios for each approach are provided according to their characteristics. Moreover, prediction accuracy affecting factors are analyzed and corresponding approaches for dealing with mispredictions are discussed in detail. So here we can see the block diagram representation of the EMS of on PHEVs. So it has two types, fuel based EMS and optimized based EMSs. In fuel based we can see the deterministic RBEMS and fuzzy RBEMSs. And as for optimization we have three parts known as global optimization based, real-time optimization and local optimization. In global optimization we can see the dynamic programming, boundary mechanics minimum principle, stochastic dynamic programming, genetic algorithm, particle swarm optimization, aerodynamic traffic flow model. And as for real-time modulation time, equivalent consumption minimization strategies. And as for local optimization, we have model predictive controls, AI-based EMS and DCR-based EMSs. So we can simply see the one of the type here. Here we have used the DCR algorithms, which recognizes the current driving conditions, and in this condition we can calculate the velocity time series in the next few seconds after selecting an optimal control sequence from the control sequence as a feedback or the controlling of the system. It gives signals to the EMS based on DCR. Here the submission of the unchanged working condition in the next few seconds. We can see the graphical representation of the history and the future of the prediction of the system controlled by the control sequence. In order to cope with global concentrating issues like energy crisis, air pollution and health problems brought by conventional vehicles, electric propulsion systems as a secondary energy sources are added into the conventional internal combustion engines known as ICE basic powertrain systems to form HEVs and PHEVs. In these hybrid powertrains, the secondary energy sources can assist ICEs to always run in high efficiency area and improve the dynamic performances of vehicles. Consequently, benefiting from such powertrain configurations, dependence on fossil fuels is reduced and thus less exhausted gases will be emitted. Future driving conditions like disease prediction is the basis of the corresponding predictive energy management strategies. For HEVs or programmed HEVs, and the quality of prediction results greatly affected the performance of PMSs. This paper presents a comprehensive study on driving prediction techniques. Full cell vehicle or FCV is known as an electric vehicle equipped with FCS. Integrating FCS with battery or UC is a well-known method to mitigate FCS limitations. Battery or UC composition as a hybrid power source which represents the term of fuel cell hybrid electric vehicle. provides the FC with advantages of high energy density and high dynamic response. In such combination, designing an optimal energy management strategies plays a vital role in success of the FCHV supervisor system. Whereas finding an optimal EMS or FCVs through conventional control techniques is a well-researched topic, there has been far less work on the still challenging tasks of optimal EMS designing problems which faces FCHEVs. Having our experience in FCV power training developing in hand, we try to purpose EMS to work out the issues associated with the FCHEV power trade as a constrained multi-objective power plan while integrating fuel economy improvements and vehicle targets. In a HEV, the extra power provided by the electric motor may allow for a smaller combustion engine. The battery can also power auxiliary loads and reduce engine idling when the vehicle is stopped. Together, these features result in better fuel economy without sacrificing performance. The first is global optimization, which focuses on minimizing the cost of the entire driving condition and applies optimal control theory to achieve a global solution. The second is instantaneous optimization, which aims to minimize fuel consumption and other parameters at each moment of the drive cycle. Go easy on the accelerator and press it lightly, consistently to keep the car in EV mode. Use the ECO mode to get battery fuel economy. Brake gently and early to allow the EV mode to operate longer. Use cruise control to maintain even speed. Here we can see the energy management system of the EV vehicle control systems. We have the PMFS with H2 tank with air ventilators, battery and supercapacitor banks to store the battery and avoid the reactive powers. Low SOC or high HOC based on DC to DC converters. We have DC link, DFC, PESC and BWH with test drive cycle and DC to AC inverter to electric motor. Whereas the HEVs equipped with 2 or more energy, there is a key technology to determine vehicle power for NHAPC. The aim of EMS is to distribute the energy sources to drive the vehicle, which leads to both the fuel economy and system durability. Management can be divided into 3 categories. UL-based strategies have advantageous implementation and high robustness, which are wide including deterministic rules and fuzzy rules, which energy source through preset rules. Here, which reasonably allocate the power of each energy source through preset rules and mainly based on engineering experience. The optimization based strategy derives the optimal power allocation strategy by calculating the optimal cost function, including dynamic programming, countergenis minimum principle, equivalent consumption minimization strategy, and model predictive control. The DP algorithm is a classic offline optimization method which can solve and obtain control effects with the theoretical global optimum. However, it relies on prior knowledge of the driving cycle and the curves of the dimensionally amplify the computation burden. Fuel cell vehicle also originally a vehicle powered by a fuel cell solely, since output voltage of the fuel cell was not very stable during operation. A DC-DC converter was connected in series of the electric circuit to ensure the output voltage could be a constant value when the input voltage fluctuated within its ranges. Then a battery which acts as auxiliary power was connected with the fuel cell system. Large part of the energy is spent on braking, especially on urban roads. When the car is in motion, in recent years it has been proposed that the ultra capacitor parallelly connected within the DC bus can recover the braking energy of emergency braking. What is more, it can also improve the cold start performance of HGFC and optimize the acceleration performance. However, due to the complexity of structures and control objects, the fuel hybrid vehicle is selected in this paper, so the fuel cell and battery should be considered the power distribution. An output variable K which represents the ratio of the output power of the fuel cell in the required power. They compares the dynamic and economical performance of the HCHE. Thank you.